Hello, hello, hello. So all set. So let's start the session, right? Let me just get the link. Okay. So let's create one also. Okay, so I am just creating this mail link in order to have this. I'm saying this link I am creating just in case if there is some stuck kind of thing in between this the first hour, because sometimes this Google Meet actually stops us to go beyond 1 hour or 55 minutes of time, right? So that link I am putting in the chat box. Okay, just delete that link. No, not this one. I can share this link. Oops. And right. Now I can have this meeting link. Okay. So this is our link. So I am putting this link here. In case something fails, please join through this link, because after 1 hour this Google Meet doesn't allow, right? So still we are having some time. Just started 7 o'clock, so 7 to 9 we will be taking this class. Okay, so let me just see if things are fine. Yes. Okay, so this is week 5 of the course Transport Phenomena of Non-Newtonian Fluid. Uh, and in this particular week there was discussion about pipe flow. So as we know that whenever a fluid flows through a pipe, we just set the right. So let me just set this so that I can write. Right. So where is this? Uh, yes. Let's start the pandemic. It is connected. It is not. Now it is connected. Yes. So, so the pipe flow that I am talking about is this one. Whether I can use this one. So the pipe flow that mostly we study, where we are actually getting the velocity profile equals to max 1 minus r by r square. Okay, this in that case this is z axis, this is, and this is r, right? So this is also. So you have to just shift it a bit. Okay, so what I'm saying is just yes. So this is Z. This is R. Let me just see if things are okay. So let's present the entire full screen. Entire screen one. Share. Okay. So what I'm saying is, if I can just prompt it up, and if I can pin it, okay, now it is okay. Oh, not this one. Yes. So okay. I just want to fix it here. Yes, it is fixed. So this pipe flow uh, we are talking about. So in this particular week, there has been discussion about pipe flow, and if you see the pipe flow, which is having parabolic profile in case of this Newtonian fluid, that may not be the same case for the non-Newtonian fluid. So in entire week, there has been 4 lectures, and starting from the first lecture, different non-Newtonian fluids has been considered and studies have been done based on the models that we have discussed in the first week of the course, right? So for example, the same pipe flow for which for the Newtonian flow, you are having this u equals to u max 1 minus r by r whole square, where this u is the velocity, and then the whatever profile that you are having, this is the parabolic profile for this velocity, which is u r, and then this shear stress and strain profile you are having, right? So shear stress profile, right? So this one, if for the non-Newtonian, so non-Newtonian, if you remember, we have discussed that uh, uh, this is the standard curve that is being used for shear stress versus shear strain uh, data, and here you see that this Newtonian fluids. Let me just yes, so Newtonian fluids are having this tau. Okay, Newtonian fluids are having this tau. Uh, if I can pin it much down, no issues. Newtonian fluids are having this tau, which is varying linearly with this shear rate, which is du by dy, and here the slope is 1 and equals to 1, right? And here you see that there is this increasing slope, then there is this decreasing slope. For pseudoplastic, increasing slope is for dilatant fluids, and then this Bingham plastic is there, and the examples, for example, toothpaste is Bingham plastic, right? Bingham plastic, and then this pseudoplastic is the latex paint that you are having, and dilatant is the water or cornstarch. Cornstarch is a dilatant fluid. Okay, so it is here. Pseudoplastic is shear theory, and cornstarch, water and cornstarch mixture is a shear thickening, and toothpaste, you know, it is Bingham plastic, right? So, so for the case of toothpaste, there will be yield stress. So the you have the first lecture of the week was about this, where you got to know about this power law fluid. So when we are talking about power law fluid, there we are having n equals to 1 and less than 1 and greater than 1. All these three cases have been dealt in week 1, and if these fluids are flowing through uh, pipe which is having D by L ratio very L by D ratio very high, or D by L ratio very low, in that case how the value of n is coming up into the velocity profile and flow rate, and how these are actually dictating the overall behavior of the fluid, right? And then there was another model, LI's model, which is mostly being used for this. So if you remember about the LI's model that was there in the week 1, so you know that when it is applicable, and that Alice model equation has been utilized uh, for solving. So every time whenever we are solving, we are starting with this Cauchy's equation of motion, and then in that Cauchy equation of motion, the shear stress tau. In this case, the tau RZ is the important thing that is being considered, and rest got omitted because of the system that we are dealing with and the kind of coordinate that we have used for solving this. So this is it for this particular thing. So all these power law, then LI's model, then Bingham plastic model, and then this Hartley-Berkeley fluids, where this which is Hartley-Berkeley fluid, and this this Bingham plastics model. In both models, there is this tau equals to tau b Bingham with the threshold constant, and then plus yield stress plus what, this mu times du by dy. But if this mu times u by dy is having power of n, along with this tau naught b, in that case you will call it tau naught b as yield stress as tau naught h for this Hartley-Berkeley. So the derivation becomes a bit tedious. So entire week there has been similar kind of approach applied with different constitutive relations for tau that have been developed for different kinds of fluid under different limits, and that has been utilized for evaluating the final velocity profile and relating the velocity profile to the volumetric flow rate, and in turn this volumetric flow rate has been connected to the pressure drop which is across the pipe, that is actually driving the force. And we came to a place where we are able to see that there was this discussion that if you are pushing a Newtonian fluid with a given volumetric flow rate at a given pressure drop, if you are having some other fluid which is non-Newtonian in nature, for example these fluid which is pseudoplastic, dilated Bingham plastic, these fluids will be behaving different. Their flow rates will be different as compared to the one that we are actually having with the Newtonian fluids, right? So what I am saying is, if you see this particular overall lecture here, what I'm saying is, just you see this, okay, it is good. So this was the one we have talked about, and this relationship is changing. This is for Newtonian. For them, this is different. That can be expressed as power level, but then for this one is different, and then something other than this, like viscoplastic fluids, viscoelastic is another limit which is not dealt here, and time independent is another limit which is not here. It is only generalized Newtonian fluid which is time independent in nature, right? So in these things, if you see that whatever fluids we are dealing with in the real life is non-Newtonian fluids. Most all the fluids, whenever we are considering the Newtonian fluid, these are hypothetical. And again, these are only assumed or closer to the Newtonian. But mostly The fluids are non-Newtonian in nature because of the abundance of effects and behavior that are possessing them, right? So if you see this, with this, if you see the next slide. So for this one, if you see this, shear stress versus strain curve, pseudoplastics are here with the decreasing slope. See, Bingham plastics are here, dilatants are here with the increasing. So let me just see if somebody came in. So I can just, okay, stay in the call. Okay, so okay. So ideal fluids behave more like a fluid. Okay, so if you see this, the things are very easy in some sense, but is equally difficult in some other sense, right? So if you want to actually deal with these things in detail, then you have to actually develop flow equations through pipe for a given system like we are having in this case the pipe, uh, and to have this in hand, right? So if you see this particular thing, then you can see uh, many other important aspects of the food, right? So let me just so what we I will be doing, I will be actually starting with the week one, and for each week there is some 3 to 4 questions that we will be solving, and these questions will be helping you in solving the assignments that you are given with, and the final examination you may be facing the same questions, right? Overall, the main purpose of this particular lectures are to help you in actually going through the degrees equations that are there. So these equations are derived using base governing equation that you can refer to in any books. So you no need to memorize them, just to understand the concepts of them, right? And whenever a question is framed, they will be conceptual in nature. You don't need to memorize the governing equation, those things, just some idea about the final expressions and the boundary conditions you will be sailing through the entire content of the course, right? So if you see, another thing is here, this is stress versus strain. Here this another curve is coming up, which is viscoplastic in nature. So these viscoplastic curves which are there, they can be explained through the Hartley-Berkeley formula. So all the 5 models of time-independent fluids are coming up into the picture to their respective stressor, shear stress versus shear rate curve, right? So this picture I have taken through Google. So uh, that is there. Another one also I have taken through some Google, right? So these are some questions that we will be solving in the course of this particular lecture, and I will be giving some questions to you also that will be definitely helping you in picturizing the whole content, and it will definitely help you to actually understand the concepts taught over this entire week in a deeper sense, right? So let's begin with this lectures. So let me just put the slides of the course, because why I am using directly slides. So to keep the content intact here, the content is used. Equations are very big. So like entire 4 lecture of the week, we are actually going to revise it within this 2 hour framework. In that, we will be solving some questions also. So that's why I'm referring it in order to preserve the writing time of the TDS equation, rather to discuss concepts in detail, and then we will be anyway having a recapitulation of all the concepts that has been taught in the class. So, so the week one was around first the recapitulation started, flow of the being a plastic fluid. So week one, let me just open the week one. So this is the solution of the question that we will be solving here. So let me just, so first question of the first slide of the week 5 is this one. So flow of the power law fluid through circular this tube due to pressure difference, right? So if you see this, how you are actually going to sail through this is uh, uh, the basic assumptions will be a Newtonian fluid, how it is flowing through the pipe. It is the standard question that people solve in the basic fluid mechanics course, right? And basic transport fluid. But here you are dealing with the advanced transport fluid and advanced fluid mechanics course. And here, if you see the flow of power law fluid uh, uh, through circular tube due to pressure difference. So if you are able to do this, then you will be able to explain something, some concept related to this. This three fluids, which were this pseudoplastic and Bingham plastic and Newton. So these three will be coming into the picture once you are able to derive the standard expressions for the power law fluids, right? So the basic assumptions are infinitely long cylindrical tube that I have already said, and then flow is laminar and incompressible. Gravity is not considered, and isothermal condition has been employed, right? So steady state, any time derivatives will be going to the zero. So it is equilibrium state. After equilibrium state, you are actually talking about symmetric in theta direction. So there is axisymmetric in nature. Okay, fully developed flow. So any properties with respect to z, with respect to theta, with respect to time, you are putting it to the zero. So flow is in z direction as a function of r, right? So vz will be existing, which is the function of r, and v theta and vr you are taking them to be zero. So to keep the thing simplified in nature. Now the next slide was equation of continuity. So you took equation of continuity and then you started actually probing different terms, and you came to know that actually in this one I cannot highlight, right? But I can highlight. Yes. So these will be highlighted. No issues. Okay. So steady state, so this will be zero, and then you are not having this VR, so VR will be zero, so this will be becoming zero. There is no property change in theta direction, so this is becoming zero, and then this is also zero because of the fully developed situation. So now you see that continuity equation is satisfied, right? So this is very important because this part is in all the 4 lectures, right? So basically you are actually looking at how the equation of motion and the continuity equation is used. These equations you are directly taking from the standard books, like you have derived it in the week 4, the Cauchy's equation of motion, and these all are Cauchy's equation of motion in radial coordinate that you are actually looking at. And similarly, if you see R component of the equation of motion, this is going for because of the transient nature of the system, and again this is going, VR is 0, right? So this is 0. V axisymmetric, so del V theta by del theta is 0. Then V theta is 0, right? VR is also 0. Vz is not 0, but VR is 0. That's why it becomes 0. Del P by del I, we cannot say anything. And this VR is 0. So here this will be becoming 0, right? Okay, so this term entirely becomes 0. Axisymmetric, this is 0. This is also 0 because of the symmetry condition, and this is 0 because of the fully tripled nature, right? And gravity you are not considering in nature. So through this equation you get del P by del R equals to 0. This says that your P pressure is not the function of R, right? Now if you actually look at the next theta component of equation of motion, here also similarly if you see, this entire terms will be going to 0, right? And then del P by del theta you cannot say anything, but you can surely say that VR is 0, V theta is 0, so this will be 0, right? And this is also 0 because of the axisymmetry nature, this is because of the fully developed nature, and this for the laminar flow you know that symmetric flow situations are there, so this is equal, so this becomes 0. Gravity is not considered the last term. So from here you can see that del P by del theta equals to 0 means P is not the function of theta also. So from the R momentum equation we got P is not the function of R, and from here we got that P is not the function of theta, so P is not the function of R and theta, right? So now only the dimension that is remaining is Z, so P must be depending on Z, and through Z momentum equation we will see that this is true, that this part is entirely becoming 0, right? So this is 0, this is 0, this is 0, right? All the terms are becoming 0, this is 0, this is 0, right? So entire thing is 0, and now if you see that from here you cannot say anything about this because VR is 0 but VZ is finite, so this will be finite, and this is 0 because of the axisymmetry, this is 0 because of the fully developed flow, and this is 0 because of gravity is not considered. So you get that del P by del Z equals to this. So this entire term depends on R, and you know that P del P by del Z here. So from above you got P is not a function of R, so this P is not the function of R, but these terms are remaining on the R. So based on that, so P is not the function of R, and this is del P by del Z, so this is also not the function of R, right? So this must not be so individually you can solve these terms. So P is the function of Z, right? And RHS is a function of R, right hand side. So thus we can write ordinary derivatives here, right? Because they are not partial, right? And now once it is ordinary derivative, you say that P is Pz only, and right hand side is independent of Z, right? So you can solve them separately. We can integrate del P by del Z to obtain this. For the time being, you consider them as C1. So this P equals to C1Z plus C0. You got it? Now at Z equals to 0, which is the center of the pipe, right? You are having P equals to P0, right? And if Z equals to 0, you are having P equals to P0. It will give you P0 equals to C0, right? And at Z equals to L, right, P equals to PL, right? So Z is, you remember the kind of geometry we are dealing with. The geometry we are dealing with is the same that I have drawn. So we are dealing with this kind of geometry, right? We are dealing with this geometry. So here Z equals to 0, here P0 is the pressure. So here Z equals to 0. So P0, suppose this is L length, it is PL, Z equals to L, and based on the for the R you are having different conditions, right? So if you see this, then what I'm saying is this P dot, let's take it somewhere else. Okay, no issues. So yes, so this you got that already, and now if you see that If you have at z equals to L, P equals to PL, you are having this C1 and C1 equals to this, and then you back substitute them, you will get P expression to be like this, and from here you are having del P by del Z as a C1, which is del P minus P0, PL minus P0. Means what? Across this pipe flow, PL minus P0 divided by this L is the diameter that you are actually, del P by del Z that you are actually dealing with, right? So since right hand side is a function of R, only left hand side is independent of R, right? We can integrate right hand side of the equation 1. So this is the equation 1 that we have, right? So if you see that, so let's integrate that. So this is the equation that you got. Del P d r tau r z dz equals to r dp. So this r you just add it here. This r. So this equation z component of motion you are talking about. And when you solve this from here, tau r z is coming to be this, and you see this particular expression. If you wisely look at, you will come to know something very interesting. So at r equals to 0, this tau rz is becoming infinite, right? Because C2 by r is becoming 0. C2 by r is becoming infinite, means r is 0. So continuum hypothesis says that any flow variable and property of the fluid will not become undefined or infinite in any region in the control volume, right? So this is violation of this this continuum hypothesis for the low Newton number, right? It means that for R0, if this equation has to be satisfied, C2 has to 0. That's why here you take C2 should be 0, because tau rz has to be finite value, and dp by dz you already derived in the backslide, p naught minus pl by pl minus p naught by l. Okay, so when you resubstitute it C to 0, you got tau rz equals to this, which is in front of you. And at the wall, if you calculate it, that small r is changed to the capital R, right? So if you actually look at this, then the main thing is, if tau wall you calculated, tau as a function of r you got in terms of the initial junction pressure to the later junction pressure, cross section pressure. So now till now you have not considered the kind of fluid. So nowhere you started with the Cauchy's equation of motion and you assumed different assumptions that you had, like laminar flow, neglected the gravity, incompressible fluid, axisymmetric, fully developed flow, and then steady state. And under those assumptions, you got to know that these expressions are coming for tau rz and for dp by dz, right? Till now, there is no assumption of nature of fluid. It means that this is a general expression that can be utilized for any kind of fluid, whether it is Newtonian or whether it is non-Newtonian fluid. So we will be utilizing this. So this equation 4, equation 3, those things means anything we have talked here. This slide, this slide, this slide, this slide, this slide, this slide. Okay, so from 1, 2, 3, 4, 5, 6, these 6 slides will be applicable for all the lectures that we have in the particular. Okay, right? So now onwards, there is this this one thing which is coming up into the picture. Now you are imposing the condition and the constituted relation for the power law. Right? Okay. So this, if you see this, it means this. So this cursor is visible, yellow color cursor. Let me just okay. So this tau rz equals to m minus dvz by dr to the power n. So this is power law model. Power law model is having this indexes, behavioral index and consistency index. So now if you see this, as you replace this dp by this tau rz equals to minus p0 minus pl divided by 2l r that you derive here, if you put it like this, slowly I am going for this particular lecture, but once I will be in next 2 lectures, I will be a bit fast because we have to cover the entire content and revise them. But here I am a bit slow. So you just put this tau rz value, which is derived from the power law here. In the equation 3, you will be getting this. And just rearrange it, divide both sides by 1 by n, and then have m this side and divide 1 by n. Take power 1 by n both sides, you will be getting it. And Vz is this, right? Plus C3 once you integrate it. So you know that, till now you know that if this Vz, so it is very easy. Till now we got to know that tau rz is P0 minus PL divided by 2L R. So you got to know that this shear stress is a function of R, and this is the general equation. So these two equations, that the tau rz shear stress and this dp by dz equals to PL minus P0 by L. This is applicable for any kind of fluid. Till now we are not having any assumption of Newtonian fluid or anything. We started with the Cauchy's equation of motion, and Cauchy's equation of motion we had. These red terms became zero because of the conditions and assumptions that we had: steady state, symmetric, and the fully developed flow condition. Under the limit L by D ratio very large and neglecting the gravity, isothermal condition, laminar and incompressible fluid. So only Vz velocity is there because it is a pipe flow. So through the pipe your flow is happening. And as in the case of laminar flow, there will be formation of this parabolic velocity profile. In the case of different fluids, which is not Newtonian in nature, the fluids that we have talked is power dependent fluid. So let me just again put that slide. So these fluids that we were talking about, so pseudoplastic, dilated, Newtonian, these fluids. So we have to use the constitutive relation for tau rz in the expression, in the general expression that we have derived, and we got to know that for example, toothpaste, water and cornstarch, the mixture of cornstarch and water and then latex paint, they can be, for them we can derive the velocity profiles, right? And that is the agenda of this particular week, right? So let's just come to the slides that we were discussing here. So these equation, the equation dp by dz PL minus P0, you just remember this for the next 4 weeks, 4 lectures, because in the entire week we were having this as a set of equation, and only we were replacing tau rz, this tau rz based on different model. For example, we are having power law fluids, then this tau rz is represented as this. If we are having Bingham plastic, then they will be tau naught plus m minus dvz by dr. When we are having Hartley-Becquerel fluid, then this will be tau naught h plus m. In the Hartley-Becquerel, the second term is having this same exact thing, where the power law is also there. So the derivations become tedious because of the presence of consistency index and the behavioral index, at the same time yield stress, but the algorithm remains same, right? So once you had this equation, which is the general equation for any kind of fluid for tau rz, and then for a given system you are having this, just rearrange it. After rearrangement we got that, divided it with m, you get it here, and then divide the whole equation by 1 by n, and then you got to know that Vz is here. So del V Z by del Z, del R you solved, and you got that Vz is this one. You know that at r equals to capital R, your velocity going to be 0 because it is a pipe flow. So at the wall there will be 0 velocity. Through that you back evaluate the C3 and then we put it here. Finally you are having velocity profile to be this, and you can see that our velocity profile, the equation 5 is depending on this n, right, and m. So these are the power law exponents which are coming up into the picture. And then now using this Vz you can derive this volumetric flow rate, and the main agenda is you evaluate the velocity profile, you evaluate the volumetric flow rate, and then that volumetric flow rate you convert them or connect them to the pressure drop. So once the pressure drop information you are having, because that is actually getting pumped, so if this pressure drop is connected to the volumetric flow rate, then this pressure drop is different for different volumetric flow rate. What I am saying is, for example, if a Newtonian fluid is flowing at a particular pressure drop, suppose a pressure drop of suppose like 0.1 atmosphere you put, right? Suppose 0.1 Pascal pressure drop you have given for a Newtonian fluid, and you are having X volumetric flow rate, right? If the same pressure drop 0.1 you are giving for the power law fluid, for example pseudoplastic Newtonian, Bingham plastic, or this viscoplastics, right? So these they will be having different volumetric flow rates at a given pressure drop, and their velocity profiles will be different. Within the, if you look at the flow in the pipe, the velocity profiles will be different. Why? Because of their rheology that they are having. So the constitutive relation we have already talked about in the second week of the lecture, that any deformation in a fluid, right? Any deformation in the fluid is explained through a relation, and that relation is the constitutive relation, right? So these constitutive relations are actually whatever expressions you are having for the shear stress, they are relating them to the shear strain based on the rheological property of that particular entity that you are talking about, right? So let me just see why these troubles are happening. So somebody asked some question, sir, how the flow rate changes with different type of non-Newtonian fluid. So that's what we will be deriving in this course of lecture. So what I'm saying is, if you see this particular lecture, let me just put it this, if I can pin and pin like this. So if you see this one, so this is, we have taken power law fluid. So if we change the value of n, then the fluid property will be changing. We can change it to the dilatant and the pseudoplastic, right? So now we have derived that our velocity profile is depending on n, right? And this velocity profile, through this velocity profile we have derived the volumetric flow rate, and this is very just tedious equations are there, but the final expression just you look at is q is depending on n and m, right? And finally through this volumetric flow rate you wanted to relate this volumetric flow rate with the pressure drop, and that can be easily done because you are also having dp by dz to be dp by dz equals to pl minus p0 by l. So once you derive it, I am coming to the main question that you have asked. You see here, suppose your fluid is Newtonian fluid, right? So here you see that this Newtonian fluid which is having n equals to 1, the velocity profile is parabolic in nature, right? But if the value of n is not 1, rather it is 1 by 3, then in that case this 1 by 3 and n is less than 1, and this case you see that your velocity profile is becoming flatter in the central region, where in the case of Newtonian you was having maximum velocity profile. Here there is a kind of plug flow conditions are coming up into the picture, right? And if n is 3, there is this cone kind of phenomena is happening, right? So it is not the pipe or the pressure drop, it is the fluid that is flowing through it. So if it is pseudoplastic or dilatant, fluid, for them based on the conditions that we have derived here, the volumetric flow rate, the velocity profile, and now after that, if you are having velocity profile, volumetric flow rate, then this dv by dz equals to del p, this particular thing. That this is nothing but you just replace del p by del z with this particular expression p0 minus pl by l, and when you resubstitute things here, so in the expression of q, you see this is coming up into the picture, right? And if you actually represent this shear rate, in terms of the above conditions, and do this mathematical jugglery, you are going to get the shear rate depending on the q value along with the coefficients that are coming up because of the power law, right? So this tau w to the shear rate data is useful in analyzing capillary rheometer data, right? So now if you see that, based on that, just once you got the velocity profile, you use that to calculate q through the integration, and once you got this q, you wanted to relate that q to the pressure drop. So again you started calculating v average velocity, and then you started calculating, what I am saying is, average ratio of velocity to the maximum velocity. This ratio is also important, because in the case of pipe flow, as we know that we calculated u max, right? So sometimes people say that u max divided by u average is equals to 2 for the pipe flow. But what about this value if the fluid is different? So in that case, this ratio will be depending on these exponents, 3n plus 1 by n plus 1, those things, right? So this 3n plus 1 by n plus 1 is the maximum velocity kind of thing will be coming up into the picture. So for the Newtonian, like you had this, so suppose this equation, general equation you derive for the non-Newtonian fluids, which is the power law fluid. So here if you put n equals to 1, then 4 by 2 is 2. So your Newtonian flow condition is also getting verified that the maximum to the average is 2, right? So just these tedious equations are there. Mathematically it is a bit difficult, but the steps are same. In the case of Newtonian fluids, in the basic fluid mechanics course and the basic transport phenomena courses, people just go for the Navier-Stokes directly. But here for this particular course, you are not starting from the Navier-Stokes equation, because Navier-Stokes equation is already having this assumption of this shear stress, right? But this Cauchy's equation of motion you are starting with, because there is no assumption. Is the graph for the laminar flow or true for turbulent as well? No. For the turbulent, there will be some different aspects coming up into the picture. So that, I think that is the part of 7th or 8th week. So turbulence is entirely different aspect. So let me just reread the question. Is the graph for laminar flow or are true for turbulent as well? No. So in the case of turbulent, chaotic nature of the fluid flow, and again in the turbulent, if you are having non-Newtonian fluids, then that is another level of complexity that you are putting in. So till now, I think in the 7th week there is some analysis that we will be doing about the turbulence. And again, even this course is not actually fully covering the concepts related to the turbulence, and some more advanced courses will be needed in order to actually deal with this transport phenomena of non-Newtonian fluids in turbulence. So that may be very interesting to see, right? But this laminar flow situations just we have opted for, because you can see that the kind of mathematical juggleries we had to go through even in laminar flow with lots of assumptions, right? So that's what we are going to do. So we derived this u max, u average, and then velocity profile, volumetric flow rate, and then how these velocity profiles are related to the pressure drop, right? And also how the volumetric flow rate that we were having, this volumetric flow rate is getting themselves linked to the pressure drop, right? This is the pressure drop, this is the volumetric flow rate. So these informations are very important. What so till the third week, what we did, so I just wanted to tell you that any non-Newtonian fluid we are dealing with, they are we don't know anything about them. For example, what is the shear stress versus shear strain relationship for them, that will be computed through the capillary viscometer and the rotational rheometer, right? Once you are having that shear stress versus shear strain data, based on that you are going to see or fit it for different kind of models that you are having. For example, you are having power law model, or you are having this Hartley-Berkeley fluid model, or Bingham plastic model, right? Or dilatant pseudoplastic, those things you are having. Once you, through that data, shear stress versus shear strain data that you got, you fitted it for what reason of shear rate your data is. For example, what I'm saying is, if you see that this particular diagram, if you see that here is suppose here you are having 10-second inverse, here you are 100-second inverse, right? For example, till 0 to 10-second inverse, your fluid is behaving as something pseudoplastic. So via fitting you can get, and afterwards your fluid may behave as suppose dilated, right? Your fluid may have for example this kind of shape. So based on that, for that particular range of shear rate, you are having a fitted constitutive relation through different models. For example, Bingham plastic model, pseudoplastic, or Hartley-Berkeley fluid model. And for that shear rate range, you are actually solving for, and based on the expressions that we have derived if you are dealing with the pipe flow. So all the expressions that we have derived till now in this particular week was the pipe flow. So till now you had got that pipe flow, laminar pipe flow, Newtonian fluid you already did, the parabolic profile. But in the non-Newtonian case, we came to know this one. You see, if your shear thinning fluid is there, right? If the shear thinning fluid is there, it means if you are having pseudoplastic, then there will be, the profile is flatter at the center, right? And if you are shear thickening, then profile is sharper, so corners will be coming up, right? So this is U max to the U average 3n plus 1 by n plus 1. So through this also you can see that if n is 1, right, so it is 2. So you can see that for n equals to 1, the maxima is here 2, right? When n is 1 by 3, it means 1 plus 1, 2, divided by 1 by 3 means 4 by 3. So if you calculate, you will get something that 1.5 you are getting. So for n equals to 1 by 3, 1 by 5. Okay. And then for n equals to 3, you are getting this one, which is 2.5, right? So through this particular analysis that has been done for the power law fluids, which is actually dictating us for n equals to 1 and less than 1 and greater than 1. So far we have not considered the fluids which are having this this yield stress, right? What is yield stress? We have already talked about. Is yield stress is this value, right? This value, yield stress, right? So if you see that, let me just see if somebody came up, right? No. So no. So this is yield stress, and this in our models tau naught B for Bingham and tau naught H for Hartley-Berkeley fluid. This is coming up into the picture. So if you remember the things that we have talked in the second week, many times I am rewriting the equation. So tau naught tau equals to tau naught B plus mu du by d r or dz, something, right? So this is for Bingham, right? When tau equals to tau naught H, then there will be this dependence of tau. This is what? Hartley-Berkeley. and when only this is there, then this is power. Power law, right? So these are the constitutive revision which is going in from the measurement of rheology of the particular fluid and then fitting, right? So now let's see what happens to, so this we have talked about, right? So from here you can see that the pressure drop is directly proportional to Q to the power n, volumetric flow rate to the power, right? For shear thinning fluid, n is less than 1, right? Pressure gradient is less sensitive than for the Newtonian fluid to change in the fluid, right? So for the Newtonian fluid, Q is 1, and for the shear thinning fluid, right, n is less than 1. So delta P will be less sensitive to the flow, right? Sensitive for flow rate, right? And similarly, for the same n equals to less than 1, n is less than 1, the flow rate shows a stronger dependence on the radius of pipe. You see that if n is 1, then n is 1, then it will come out to be 4. And when n is less than 1, it is coming out to be 5, right? So based on that, we had one example here. The direct expressions has been utilized, whatever expressions we have solved, and then we came to know that these are the lectures that we are doing. So this was the question that we have solved. So now onwards, I will be just dictating the expressions, final expressions, and then the way we have derived. So this particular slide we have discussed very clearly. And now onwards, we will be focusing much on the questions that we are going to solve in this particular week of the live class, right? So the first question that we are going to solve is this one. You see, let me just, so this is visible, no issues. If I can set it into this. So nothing is happening. No, don't minimize it, rather into the screen myself. Right? And now I want to just add this. No issues. I just want to, yes, it is okay. Now it is set. Okay, so the question is a polymer solution obeying power law model m equals to 5 Pascal SN, right? We just have this here, right? Uh, okay, so if things are okay, let me just see if there is no reminder. Now, if this power law, a polymer solution obeying power law model m equals to 5 Pascal second to the power n, and n equals to 0.5, right? So you got this m and n is flowing through a pipe of diameter 15 mm, then this length 20 meter at a volumetric flow rate of, this 10 to the power minus 6, right? It is 10 to the power minus 6. What is the corresponding pressure drop in kilopascal, right? So just look at the values which is given here. So you are having this m equals to 5 Pascal these units are very important, right? Equals to 0.5, and then you are having this volumetric flow rate to be 5 into 6 meter cube per second, and you have been asked about the delta P in kilopascal, right? This is the question you are asked about. And what I'm saying is you have to actually look at this very carefully in order to actually have clear cut understanding of the things that are being asked over here, right? So it is now important to actually solve these questions and then relate it with the content that you already had, right? So now if you actually want to solve this one, then you have to be referring to the questions that we have just derived. So for the time being, I'm just putting the solution here for me so that things become easy, because I will be today solving these questions a bit faster, right? So what I'm saying is, see this, right? So let's see. So now the expression for the q that you have already derived, that we have discussed, is pi r q n divided. So we can I'm referring to the derivation, so you can also refer, or else you can derive, but it will take longer time to actually reach to here. So that's why a bit understanding is needed, and you will be actually getting through this particular problem, right? So all the values that are here is provided, right? And uh, once you know, so r value you are having, so here they said that r is 15 mm and r is through a pipe of diameter, so it is 7.5, right? It is 7.5, right, mm, and this L is 20 meter, right? Once you put all the values that I'm going to put here is 3.14 multiplied by 7.5 into 10 to the minus 3 cube multiplied by n. The value of n you had is 0.5 divided by 3 into 0.5 plus 1. So this you want to calculate into this 7 into 10 to the minus 3 divided by 2 into 22 meter. So it is 20 meter. 20 meter into m. The value of m you got is 5 Pascal second to the power m, and divided by 1 by n, and you are having 0.5, so this will be 2. Once you solve it, the value of q you are going to get is 1.518 kilopascal. Right? So this is the answer to the question. So the options that are there, if you see that option B is correct. Option B is correct answer, right? Now moving to the next question, that is here. If you see, right, a power law fluid of power law behavior index value of 0.5 is pumped through a pipe of diameter 25 mm at volumetric flow rate of 6.46 into 10 to the minus 4 cube per second, right? So let me just take it as a power. It is a mistake here. What is the maximum velocity? So the similar question almost we are having, and now the maximum velocity value you have been asked, right? So what I am saying is, if you see that here the value of so this if you see, I think something came up. No, that is me. Okay, so this value of n equals to 0.5 like in the last question, and d is 25 mm. Here volumetric flow rate is 6.46 into 10 to the power minus 4 meter per second, right? So the V average, right, you have to calculate. So the V average you can calculate. So you know that V average, once volumetric flow is given, the pipe is like this, and you are having the volumetric flow rate through this pi r square area, right? So then V average can be defined as this, right? Pi r square. Once you derive this 6.46 into 10 to the power minus 4 divided by pi 3.14 into r square means 12.5 into 10 to the power minus 3 whole square. This will give you 1.317 meter per second, right? And once you did this 1.317 meter per second value, then what you are going to get is the one that we were waiting for, is the V average value. So now the V average value, you know that 2.195 into, no, what I'm saying is V average, you got to know that 1.317 meter per second, right? Now you know that V, like in the laminar case, for laminar, what you are having, V max to V average equals to 2, right? So here V max divided by V average, right? Let me just change the color. Okay, so this is equals to what? 3n plus 1 divided by n plus 1, right? And once you use this one, you are having it is 0.5. So for example, if you can verify, put n equals to 1, it is 4 divided by 2, it is 2, right? It is verified, right? So once you derive it, then here it is 0.5, so it is 3 into 0.5 plus 1 divided by 0.5 plus 1. Okay, it is 1.5, 2.5 divided by 1.5. So it is 5 by 3, right? So now V average equals to 5 by 3 multiplied by 1.317. So it is coming out to be 2.195 meter per second, right? So the options that are there is this one, 2.195. C is correct. C is correct. Answer. Okay. So this is it for this particular question. Next is about Hartley-Berkeley fluid. So let me just put it like this. So what I'm saying is the Herschel-Berkeley fluid, Herschel-Berkeley fluid flowing through a pipe of what? Of 40 mm diameter, right? Under the laminar flow. Okay, condition, the value of phi equals to 0.5. So phi equals to what? You know that Rp divided by capital R. It is also equals to what? Tau P divided by tau R, right? What I remember, just So these relations you need to remember, right? 0.58. So if I am correct, let me just refer the slide. So you have to refer the slide, right? So if you refer the slide, so this was the part of lecture 4. We just have that slide here. Yes. This slide here. Yes. Okay. So what I'm saying is, if you see this partial bulky fluid flow through pipe is this was the revision of the last lecture where you had this Bingham fluid. So there you derive for this velocity in the central region. There is a plug velocity, and then there is a velocity profile kind of parabolic in the angular region. Then there was this volumetric flow rate calculation. This volumetric flow rate was depending on this phi. Phi is the ratio of this RP, the transition point of the velocity profile, and then shear stress, and then also the V average you have calculated. You have calculated based on that the fanning, the friction factor, and then friction factor is through that you got to know that there is something called Bingham fluid Reynolds number, and then Bingham number you derive based on that, and then Headstrom number you also derive. So these numbers are important. So based on that, you can have some questions. So we will be always having some questions. So for now, I am just going through this. So if you see that Hartley-Berkeley fluid flow through pipe due to pressure difference, if you see the viscoplastic fluid flow only if applied stress exceeds the yield distance. So like we have already seen in our discussion about this Hartley-Berkeley fluid, uh, like here I think I just wrote, right, this one here. You say Hartley-Berkeley fluid, there is this threshold yield stress, right? And that threshold yield stress is actually uh, this applied shear stress that has to be exceeded to flow, allow the flow, right? At the middle of the pipe, tau Rz is less than yield stress. Okay, solid plug like core flow should be there, will be there. So this is the solid plug like flow is there, and then radius of the plug is Rp. Okay, and it is dependent upon the magnitude of the tau naught as a tau w, right? And these are the assumptions that you have to take in, and these slides I have told that this is same expression that you will be deriving in these cases just afterwards. So here this Rp by R tau naught h by tau w. What I'm saying is tau naught h by tau w and Rp by R, right? So just have this one. In the case of Bingham plastic, it is tau naught B by tau W, Rp by R. This is the Rp radius till where this Bingham this yield stress is actually existing, right? So let's see. You are having this problem till you are having plug flow like constant velocity kind of situation. So let's see the one that we were talking about. This one. That's what I Rp by R. Rp is the condition, and in this case, this tau p is what? Tau p is nothing but this yield stress. This is tau naught h. This is tau w, right? This is tau w. This is tau w. Right? It is at the R. It is at the R. This actually you derive. So because why? Because you already had this tau equals to what? dp by dz r by 2, right? If you remember, again I am saying that is very important. Those slides are very important. That 6 slide that today I discussed, these 6 slides So here you are having this tau expression to be dp by f, dp by d0, dp by r by 2. And if it is at r, it will give Wall-Sear state stress. If it is at rp, then it will be giving the threshold. So there has to be validations for these equations, right? So what I'm saying is these equations are general equation and they can be applied for any kind of fluid. Just you have to induce that constitutive relation in order to have the particular picture cleared in your mind, right? So with that in mind, let us see the equation that we were solving. Okay, so now you know that this was going to Hartfield still bulkily fluid. Let me just save it first. Okay, so yes, so these are okay now. So this knot should come down and this H should come up, and things are okay now, right? So, okay. So if you remember, for Herschel bulk fluid, we have derived that velocity profile. For what I'm saying is Herschel bulk fluid velocity profile at T, right, is equals to, it is the plug flow, right, equals to m r divided by n plus 1 tau w divided by m for 1 by n 1 minus psi n plus 1, right? And when you put the values that you are given with, okay, values you are given with, value of n is 0.5 multiplied by 40 by 2, right? Radius is, diameter is 44, radius is 20 by 2 into 10 minus 3 divided by what? N plus 1 is 1.5 plus 1. Tau w by tau, m is what? Tau w by m. And if you see that tau w here, tau w is what? Wall-Sear stress is given. So Wall-Sear, the walls corresponding Wall-Sear stress is what? Tau w is what? 29.31 Pascal. Right. Also tau naught h is given 17 Pascal. M is given 0.83 Pascal and N is given to 0.5. Okay. So what I'm saying is you just put all these values over here, which is 29.31 divided by 0.83. It will give you this 1 divided by 0.5, and this 1 minus 0.58 divided by 5 divided by to the power here 0.5 plus 1 divided by 0.5 Once you derive it, you are going to get that. It means this is the maximum velocity that you are going to get, and any velocity will be lower than this. So, what is the answer? 0.62 is the D option. So it is correct answer, right? Getting my point, right? So let us discuss this in the course where this expression is present, so that for you can relate to. Okay, a bit hang is happening. Let me just fix it up. Let's say it again. Okay, so what I'm saying is this one. This till now you got the same Herkel-Bernoulli fluid is this. We derived for this tau rz, and then you started. You just taken these value to be alpha and beta. So that is just one thing. But the main thing is finally what you had is this one. It was there. This is the expression that we just used in solving this. Okay, on the plug flow condition of the velocity, right? So now coming to the next question that we want to solve is this one, which actually says many things about the question that is here. Okay. Is the same Herkel-Bernoulli fluid through a pipe of 40 mm diameter under the laminar flow condition. The value of I is given same. Then what is the value of wall shear stress? What is the value of wall shear stress in Pascal if tau naught h is given, m is given, and n is given, right? So you need to calculate the wall shear stress, right? And the values you are given. Okay. So you know that this 5 is what? Tau naught h divided by, we just wrote it down the wall, right? So through this, if you see that 0.58 equals to tau naught h is given here, you see 17 Pascal divided by tau w. Tau w equals to what? 17 divided by 0.58. It will give you 29.3. Very simple question, you see. Just basic definitions you are able to solve it. It is correct. Right? Till now there is no difficult question. So such very simple expressions you need to memorize, because very simple equation through that an important equation it can come, and if it is very conceptual and needs very big expressions to be derived, the main governing equation we will be providing it, right? So you don't have to worry about the same, right? So this is done. Let's solve the next question, which is fifth question, right? And is this one rheological property of the, it is on the Bingham. So we have already solved this power law fluid, we have solved this Herschel-Bernoulli fluid based questions, and now it is the Bingham, the third lecture of. So we have solved for the first lecture of the week 5, fourth lecture of the week 5, now it is third lecture of the week 5, right? So the rheological property of Bingham plastic fluid are real, are given, and here yield stress is 15 Pascal. So you are having tau naught B value to be 15 Pascal, right? The plastic viscosity is 150 MPa. So 150 MPa. What is the approximate center line maximum velocity? It is asking about u max. If this is fluid is flowing, so the profile will be how? So for the laminar flow, Newtonian flow it is like this, but for Herschel-Berg fluid, for this Bingham fluid, so there will be this velocity profile. So at the center there we will know, and then there will be like this. Center there will be cut, and then there will be this. This is our flow, and then there is this parabolic kind of thing, right? So when this suspension is flowing under the laminar condition in a pipe of 50 mm diameter and 200 meter long, when the pressure drop is 6,000 kilopascal. Right? So when this suspension is flowing under the laminar condition, so condition is laminar. Right? Let me just see the color. Laminar flow. And pipe diameter is 40 mm and length is 200 meter. When the pressure drop is delta P equals to 640. So you got to know these informations, right? Now let's see how you are going to solve it. So you know that for Bingham plastic fluids, this for Bingham plastics fluid, what is the expression we are going to do for VZ? Maximum velocity delta, so VZ, right? So first we need to go through the lecture for the Bingham work, so that we will be having revision of the same, and then we will come to know, we are going to come and solve this particular lecture, right? Okay, so here this was the recapitulation of this Ellis model, and then this power law fluid to circular tube due to pressure drop, and then you can solve this Bingham. So this is what this Bingham plastic. So similar, this expression is a general expression. This one, the second point, it is tau Rz equals to minus delta P by L R by 2 for the pipe flow, and then wall shear stress equals to tau W equals to delta P by L R by 2. Okay, and then this velocity profile you derive for this power law fluid, volumetric flow rate you derive for the power law fluid, and then this here rate in terms of volumetric flow rate you derive for the power law fluid, and then all the behavioral index and the consistency index are coming to the picture. And then this average velocity you derived, maximum velocity you derived, and then friction factor also you are deriving. And why this friction factor you are deriving? Because it is a very important aspect. Like in the laminar flow you derive it, it gives you 16 by Re. The friction factor here is giving you similar expression, but here the Re is replaced by this, that you are calling Reynolds number for the power law, right? And then flow of Ellis model fluid through the pipe due to pressure drop difference. Similar expressions you derive for the Ellis flow also. Velocity profile, maximum velocity, volumetric flow rate, average velocity, and the friction factor for the Ellis. So these expressions you may practice with. And now these are the expressions for this. This is for this viscoplastic fluids, which is this Ellis model kind of thing. This anti-vertical fluid model also we have discussed just now, but these derivations will be same in each. These 6 slides I have already talked about. Coming to the picture now, the main aspects, right here. So here we here this is introduced, right? For the procedure of the simplifying equation of motion, we get this. This is okay. Thus, for the plug region, it is same, right? RP. Okay. And for the wall, tau W equals to this, right? So the ratio is this, and this they call it as phi. And now in the annulus region between RP to R, so you know that this is the pipe flow between RP to R means RP distance from the center is the plug flow, and after RP distance there is this laminar kind of flow is happening. This parabolic profile is coming up into the picture, and that is giving you some derivation. So the Bingham plastic fluid model you used, right? And you just did the rearrangement of this equation for the Bingham plastic, and then used this rearranged equation, right? So you are having this then when you having the you use this del T by this R by 2, right? And here you had this tau RZ minus tau 0 B by B, it's this one, right? So this tau RZ you replaced with this del P by R by 2, and this one, and then you started deriving it for Z. You evaluated C0 through the equation for addition at R equals to RP and these things. So if you see that at R equals to R, you are having Vz equals to 0, and then you calculate the C0, and then if you have to do C0, you calculate Vz, and then this Vz is valid only when tau Rz is greater than tau is 0, right? Because there is this plug where the shear stress is tau naught B, right? And for that also you need to have a velocity profile, because there will be plug flow kind of situation, but there will be a constant velocity which is will be there. So you just have to plug flow VZP. You want to calculate, just put VZ to be R equals to RP, and you will get a constant value for this, which is this one, which will be right. Okay. Okay. So right. So now these expressions we will be using. Okay, so VZP is just, we have seen how it came up into the picture, is this minus delta P by L R square by 2, R square by 4. Just see. 4 1 by mu B 1 minus RP, where the blood flow is converting them to the parabolic profile. R is the radius of the pipe, right? And once you use this, right, this is the pipe flow is like this. The blood flow and then this parabolic. So this velocity is the maximum velocity. So this will give you the U max, right? Once you convert it, so what I'm saying is you just use this expression U max equals to what? Minus delta P by L. R square means 20 into 10 power minus 3 to the whole square divided by 4, right? Into 0.15 is given. What is 0.15? 0.15 is 0.15 is then 0.15, right? Is the value of where they are saying this it is. Okay. 0.15. This is this. This is 0.14 pascals. just merely you divide by 1 right? Into this is what 1 minus Rp by R. You are having this Rp by R can be converted into tau naught H by tau naught B. And once you convert it to that, you know that this is 15 divided by this, and you know that minus delta P by L is about 2, right? This is square. And you know that the pressure drop that you are given is 650 L kilopascal and L you was having 200, right? When you put everything in this expression, when you put everything in that expression, L equals to 200 meter and delta P equals to 640 kilopascal, then Vz max equals to Vz flow velocity equals to 0.6 meters. So let us see which option is correct. Option C is correct. C is correct. Okay. In this way we have derived this particular question. So now moving to the next question. Let me just read for you. Let us see this in a way that you can actually learn many things through this particular discussions, right? What I'm saying is this one by 2 is subscript. Okay. Okay, so rheological parameter of an Ellis model. So Ellis fluid model that was just now we have seen the expressions for that, and we have seen this Bingham also for Bingham plastics derivations also to some extent. And meanwhile, with the questions we will be discussing the same. But the thing is, the kind of expressions and the process of evaluation of different parameter, be it the connection between the volumetric flow rate and the pressure drop, connection between the maximum velocity and the average velocity, and then correction between the shear rate to that of the volumetric flow rate, right, is having the same procedure that we will be using to evaluate them, right? And here the value of alpha is given 2.8. You know that what is the alpha that we will be discussing soon. So and tau half is also given. So these are the parameters that come into the LI's fluid model, right? And if you remember whatever we have discussed in the week, I think one it was there, right? So week one slide, if I can open, I can show you all the expressions that is there. So week one slide, I think this is the upside. Okay, so here if you see that these were the specifications that we were going through, and we have seen, I think, at least those questions. I think there was one question on the last question. And this is the expression. So Ellis model is what if deviation from this pseudo this PL model, this power law model is significant only at low shear rate, right? Then it is more appropriate. Where you are having this apparent viscosity by this model you are apparent or new. For Newtonian fluid, mu apparent and mu is same thing. Mu naught divided by 1 plus tau yx tau half in power alpha minus 1. So this particular expression mu naught divided by 1 plus tau ix, these things we will be actually using for our discussions, right? So for this release fluid model, right? There is mu equals to mu 0 divided by 1 plus mu this 1 plus 1 plus tau y x divided by tau half to the power alpha minus 1, right? And the expressions that we will be using for this. So what I'm saying is that we can again put this for a revision in this one, because these are coming again and again in the discussions, and then again the expressions that we have already derived for this, right? Just let me just reach to that expression and I will just put that also here, right? So I just want to take snippet to, was like, to save the time and to give you complete picture. Okay, so this is the model, and this is the expressions that has been derived in the lecture 1 of the week 5 for this. All the factors has been derived, right? And similarly for the power law also you have already derived. Okay, so I think this also I can put somewhere in the slide, because it will be a kind of revision of the formulas which came into the picture during the course of this week. Okay, so I think the power law questions we have solved here. Okay, so after this question I can put it here. Right. So this is important, and then the remaining expressions that you have derived is this one. Just put this one, just put that. This is so these are for the power law fluids. That was for the Elise model, right? And one question we have solved for the Bingham plastic, I think. So let me have that also. For the Bingham plastic we have not actually used. I think this is that. So the expressions for the Bingham plastic I will be just taking. So these are the recapitulation that are used to do in the each new classes, right? And they are actually very helpful, and those are the main expressions and agendas that are actually giving you a picture of the same, right? So just so okay, this is this, and let me just put these remaining. Okay, So another thing is, if you want to see the one that we have just solved, the Herschel-Burkle fluid, Herschel-Burkle fluid model. In that case also the very tedious equations we have derived, and those equations I think they will be provided in the exam, because it is very difficult to derive them within the span of this lectures, right? But if you actually want to go through these, right, then the things become easy. So if the equations you are having, then just some steps you are actually you have to actually derive, right? And these are the equations and expressions that we just for example, I think this is incomplete equation, but it will be a kind of revision for you. I think Herschel-Burkle equation. This was a question of so here we can. After this also there is some values. I think this is not complete. What I'm saying is, in case of Herschel-Burkle, if you see, no, not this one, this one, here, this one. Yes, this one. Okay, this, if you see this Herschel-Burkle fluid, this one. Okay, after the derivation, these are the equations, the main equations that are general in nature. Herschel-Burkle velocity profile we have already derived. Okay, this was the expression that you used, and then the average velocity that you have computed. This is the average velocity, right? Okay. In terms of Q. So these are the questions that has been given, right? So now coming to the question that we were solving for the LS model is this one, and like 2 or 3 main questions are there. Then I will give you those questions to you. It's a solution also I will be showing, so that you can solve them at your end, right? So sixth question is this one, and in this one, okay, I told you this report. No, so in this one, if you see, these are the models that is there. Okay, and these were the basics that is required to solve this, right? Now using the expressions that we have just discussed above. For this Alice model fluid flow through an infinitely long cylinder, uh, Alice model fluid flow with L by D large infinite cylinder, steady laminar fully developed incompressible flow Q equals to what? Q equals to pi r square 4 mu naught tau w 1 bar plus tau w divided by tau half alpha minus 1 divided by 4 upon alpha plus 3, right? So in the right hand side of the above equation, so these all are given, right? These all are known, and once you substitute, you are going to get. So if you see this expression was here, this expression was here, fourth expression we used, and all the values are given over here, right? These are the alpha and tau half is given, and then you are having tau w value. Okay, when you see, you are given with what? You are given with this tau w equals to what? 3412 kilopascal. L equals to 20 meter. D equals to 50 mm. So you have to see diameter of radius alpha equals to 2.8, tau half equals to 6900 pascal, and then mu zero is equals to 1.25 4 pascals. These things you have to actually, right? So now putting these values over there, let me just copy this slide where we are solving this question, right? Okay, when you put these values over there, 3.14, okay, multiplied by R is what? R is what? 25 minus 3 square divided by 4 into tau naught. Mu naught is what? Mu naught is 1.25 into 10 power minus 4, 25 into 10 power minus 3 by 4. Okay, 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 and then tau watt you are given with. Tau watt is what? Tau watt is 3412 kilopascal into 3412 1 plus 3412 into 10 power 3 kilopascal divided by this. Tau half is what? Tau half is 6900 divided by 4 divided by alpha. Alpha value is what? 0.2.8. 2.8%. Right? Once you solve it, so it will give you 2 equals to what? 2 equals to 4 into 6 by 4 centimeter. So, so the answer will be 4. B is answer, right? So 6th question is done. 7th question. This is the theoretical question, very straightforward question based on the power law derivations that you have, right? Consider a power law of known rheological parameters flowing through a pipe of length of L and uh, radius R for a fixed pipe radius of length, radius and length. What is the relationship between the pressure drop and volumetric flow rate, right? For the power law, if you remember, then you will come to know. So delta P is right equal to phi and 1. So you know that this we have already discussed. Delta P is directly proportional to Q to the power. Delta P is directly proportional to A is correct. A is correct, right? And if you want me to actually more dictate this one in detail, then I have already added some slides over here for that, because those expressions we have already derived. So here if you see, I think Q and delta P relation, if you see here, Q and delta P relation, if you see, then you will come to know about this, right? So where is that? This is Q and this is delta P. So this 1 by n means delta P is, so based on that you can see. But the thing is, this discussion was there in the lectures. Let me just put that slide because that will help you to sail through this. Right? Just, it is a bit slow, but see it. Okay. I'm saying it the same. Yes. These lectures and these slides will be available to you, and the purpose of this particular class is to have revisit of all the concept that has been taught through the questions and through some conceptual discussions, sometimes re-deriving the expression that has been taught to you, right? So these two dependencies have been explained to you. Let me just put that here. These dependencies are important in terms of solution to the problem, right? I think we are here, right? Yes. So I will just put it in the slide. I will just put it in the slide, and I will put both concepts. So two dependencies you had. One dependencies between the Q and delta P, and then Q and R, right? Okay, so based on that, you see that delta P is directly proportional to M. We had. And next is this one, the friction factor question. Friction factor is defined as what? Tau W divided by half rho V square. So this is the general expression of the friction factor. And about this we have already talked in, I think, week 1, right? So week 1 we have already talked about this. I think week 1 slide I was having. So let me just put that discussion into the picture, right? So in the week 1, if you see, let me just have this picture here. In the week 1 you see we had solved many questions, right? Starting from here, if you see many questions we have solved, and in that we had already discussed the friction factor concepts, right? So this friction factor 64 by RE and this, and how this friction factor is actually evaluated. So that those were some, but the basic definition of the friction factor was, I think, that was not the part of that particular lecture. I will be anyway dictating the same in this one, right? Just let me see if it was there. It was not there, right? So no issues, right? So you know that this, the way the friction factor has been derived, F is del W divided by what? Tau W divided by 1 by 2 rho, right? So shear stress divided by kinetic. So if you want to actually see this, Okay, if you want to actually see this in detail about the friction factor, then I can actually surely tell you about the things that we can actually solve for this. Okay, so I was having a notes about the same friction factor, and then the way it is derived and used. And that friction factor general formula that you are having, tau w divided by I will be dictating in the next class in detail, because but this is the formula of the friction factor, right? So this Walsial stress divided by half rho v square v average square. Okay, so that is there. So it is C option is the correct answer. So C is correct. Okay, it is slide 3 of the lecture 15, right? So if you see slide 3 of the lecture 15, a bit hang is there. So, the friction factor. So this is the one that so you see these are this pivot. So this is the standard here, 16 by RE. The derivations that are there, you can actually revisit them. Okay. So this is the slide where you are talk about the friction factor. So though it was for the power law fluid, but what I'm saying is the basic concepts remain same. Okay. I think we will be having 5 minutes more, because already we have solved like 8 questions, I think. Yes. So ninth question is, for a viscoplastic fluid flowing through a pipe due to pressure drop, why solid plug-like motion is found at the center of the pipe? Because shear stress at the center is infinite and viscoplastic fluid does not deform or flow if the applied shear is very larger than that of the initial. Because shear stress at the center is zero and viscoplastic fluid does not deform or flow if the applied shear stress is less than the characteristic shear. Because the shear stress at the center of the pipe is larger than the shear stress, right? All of the above A, B, C, and D. So if you see, you may see that B option is coming out to be correct answer, because it has to be larger to have deformation, right? So B is correct. So slide 5 of the lecture 16, if you see, which was about ring plastic, you will come to know, and also the expressions that you had. Based on that expressions also you can see that there is no change, right? Slide 5, we are going. Okay, so whatever is here, slide 5 of this is this one. Let me just put this, because it's very important for you to actually have a picture about the same, a feeling about the same, right? Okay, so now coming to the next question, which is the 10th question. For a power law fluid flowing through an infinite pipe, the ratio of the maximum velocity to the average velocity is what? So as you know, we have solved it many times. So it is B option is correct. And also we had this expression connected over. We discussed already in, I think, first second question. I have already told you. So this is the option. So let me just put that equation over here. So all the equations rather, I will just put all the equations again. These are these expressions that are important in terms of power law fluid. And if you see, I think maximum velocity value is there, and the ratio one, I think I have marked that it's right. Yeah, this is the question. So this is the answer to this. I've already solved this question. Okay, so you can refer to the week one of the session in order to have clear decision about this. Okay, coming to the next question. A power law fluid of power law behavior index and equals to 0.5 is pumped through a pipe of diameter b equals to 25 mm. These are equals to 0.5. While metric flow rate is given as 6.46 into 10 per second, right? So let's just correct it. What is the maximum velocity, right? So you are being asked about the maximum velocity, and now you know the expression of the maximum velocity, right? So the last question also gave the same expression, max divided by the average equals to 3 n plus 1 divided by n plus 1. And from here the max equals to 3 into 0.5 plus 1 divided by 1.5 into the average. So this is 1.67 average. It will be max, right? So the option C is correct answer, right? C is correct. Now coming to the last question of the day is for a Herschel bulky fluid to be in the laminar flow design. According to the Slatter's 1996 model, the modified Reynolds number remod should be equals to 2100, greater than 2100, less than 2100, or none of the B, C, D is true. So which of the following you think is correct? What? For the case of Herschel-Burkle model, if you remember the Herschel-Burkle model, the discussions that you had about sleep, based on that only you can say this question. This is a bit good question. If you see, uh, you need to have somewhat idea about the discussion that you have. Our Herschel vehicle fluid to be laminar in flow design according to this latter 1996 model. The modified Reynolds numbers. This kind of question can also come. So the modified Reynolds number. Okay. Modified Reynolds number RE mod should be what? Equals to 2100, greater than 2100. So anything you can say about this question. right? So this, if you see that you can, then try to dig out solve it, right? So this question I am leaving for you, and the answer to this question I will be providing. Just look at this lattice model and then come to this. So it is less than 2500, which is given. So option B is correct. And if you see this, this one, if you see, then you will actually come to know that how much important the, these discussions are, and how much where is this six? How much important these discussions are, and then how much time you have to practice these discussions so that to have a proper understanding of the same, right? Concepts. So these were the clear-cut picture about the same, and if you remember this entire week was about this non-Newtonian fluid, basically this generalized Newtonian fluids, and how these generalized Newtonian fluids are derived if they are flowing through the pipe flow, how the expressions will be derived from them, right? So that was it, and so this discussion about the Herschel-Becquerel fluid. So this Herschel-Becquerel in 1996 derived it. So what I am saying is, if you see so this is the extra state condition for the same. Let's just put it here if it is quickly. So you know that this Herschel-Becquerel model. So any background picture is this one. If you see this, I can put it here. The background picture is this one, right? The background picture is this one, right? The viscosity you derive it like this, and this is the Herschel-Becquerel where this du by dz or dr is here, and because of the yield stress and the non-Newtonian viscosity, the classical Reynolds number no longer applies here directly. But in this case, it is applied, right? So then Slattery in 1996, he actually modified the Reynolds number. Okay, and what he proposed is this. So you just go through these answers that I am giving. Maybe you can refer some research papers from Slattery, right? So what he told that Slattery introduced a generalized Reynolds number RE mod for Herschel-Becquerel fluid, right? That when K dash include rheological adjustment for yield stress and non-Newtonian index, and these forms reduced to the Bingham plastic fluid Reynolds number and the Newtonian Reynolds number in limiting cases. For example, if you see the laminar to terminal transition criteria, even with the modified definition, the critical value of the transition remains approximately same as that of the Newtonian fluid, which is 2100. Laminar flow situation, it is RE modified is less than 2100, and turbulent situation is greater than 2100, right? So So what it is, so according to the Slattery 1996 model for Herschel vehicle fluid to be in the laminar situation, this RE mod less than 200 is that correct? Okay. That's what the question was asking. This question, right? Okay, so that is it for this particular question. Just save it. And thank you so much for the kind attention. We took 15 more minutes, so because the lecture was lengthy and we were having less time for solving all those. So let us get saved, right? Now it is saved. I will be just generating the PDF, and this PDF will be shared to you, right? So these PDFs will be shared to you. It is for week 5, right? Just publishing it will take some time. But what was the main agenda of the week was, we have gone through this concepts in detail, and we have seen that how these models uh, are utilized to get the flow profiles, volumetric flow rate, pressure dependency to the volumetric flow rate dependency to this shear rate, pressure dependency to various rate, and dependencies of measurable parameters to the one that we want to address, right? So with this, I want to thank everyone, and then these recordings will be available to you uh, on the websites, so you understand that what I'm talking about. So any lectures at the MPTEL, if you see, then suppose this is the, let me just sign in. So this is the lectures. I will be signing into the same our course. So these you can access, and all the discussions in the live classes also will be uploaded there. So these 2 hour lecture will be anyway helping you in actually going through. So I will be going to my courses, right? In my courses, this the lectures that you are actually accessing through, you will be finding, right? So what I'm saying is this one. If you see this, where is this? Yeah, this is here. Uh, this, this is done. I'm just going to the course, right? So this was the 5th week. I think 6th week lecture is also here. So you are currently going to the 6th week, and these are the problem solving sessions that I'm talking about. So you can go to, and you can also give the survey to this. So you can go to the links of these problem solving sessions, right? So these sessions you can go to, and you can access these, and this is the link for this PDF that we will be uploading, right? So currently I'm not having access, so these these things you can access, right? Okay, so and meanwhile in the next week we will be discussing about this transition and turbulent flow of generalized Newtonian fluid in pipe. Okay, so this is 72 part, and the laminar flow of generalized Newtonian fluid between the parallel plates along inclined surfaces, right? And the laminar flow of generalized Newtonian fluid along inclined surfaces and concentric angular regions, right? So with this, I will be actually closing the today's lecture. Thank you so much